Assalamualaikum warahmatullahi wabarakatuh. Welcome back to our video. So we are going to see, or we are going to move on to another topic number 3, which is unbalanced three-phase systems. So this is some of the content outlines. So you're gonna see the introduction part, followed by the analysis of unbalanced loads in three-phase systems. So we are focusing on these three subchapter, namely unbalanced delta connected load, so unbalanced four-wire star connected load, and then finally the unbalanced three-wire star connected load before we come to the final part of the chapter, namely Milman's theorem for solving unbalanced load. So this is actually another approach of how we can solve the unbalanced analysis. So namely Milman's. So this is just another particular method. So you can also use the conventional as stated here. This first three analysis. Okay, 1, 2, and 3. But somehow, if the question asks you to use this particular Milman's theorem, so you have to do so. So back to the illustration over here. So the three-phase system transmission line. So it is illustrated over here, started from the three-phase generator to the three-phase load along a transmission line. So we have transmission line number 1, transmission line number 2, as well as transmission number 3 to make up this three-phase system. All right. So after completing this chapter, you will be able to explain the voltage unbalance is. So what is the voltage unbalance and its effects in power system? So we can see after this the cause and also the effects of the unbalanced system if you are having it in your three-phase system. So analyze the three-phase. You must be able to analyze the three-phase circuit-based unbalanced load 4 star as well as delta connection 3 or 4 wires phase supplies. So, and then finally you are able to apply Milman's theorems for solving unbalanced three-phase system. So introduction. So balanced system. So we have seen earlier. So what balanced or symmetrical system is all about. So in terms of phase and currents, so they have the same amplitude and phase shifted by 120 degree with respect to each other. So this is how it looks like when we come to the phasor diagram. So we have the red phase, the yellow phase, as well as the white phase. So this is the direction of rotation of your machine, for example. So with omega radian per second. So they are shifted by 120 degree from each to another. Okay, so if either of both of these conditions are not met, so the system is called unbalanced or asymmetrical. So it's either between the voltage or the currents. These criteria are not met, so the system is now called unbalanced. So typical phasor diagram of an unbalanced three-phase system. So we have the red, yellow, and blue. So the direction of the rotation, for example. So two possible situations for the unbalanced system. So the source voltage are not equal in magnitude or differ in phase angle that are unequal. So meaning, so we have the voltage at the beginning of the system or so-called source voltage. They are not equal either in the numerical magnitude, the value, all right, in terms of voltage, for example, or they are actually differ in phase by angles, right? So another possible situation is the load impedance itself. So they are not equal. So the Z value. Okay. So an unbalanced system is due to unbalanced voltage source or unbalanced load. So these are only the two possible, either it is happening or taking place at voltage source, or it is actually occurring at balanced load. Okay. So how this happens and what it costs. So because PTMB, particularly in Malaysia, as a system operator, so they try to provide a balanced system voltage at the point of common coupling, which is PCC. So between the distribution grid and the customer's internal networks. Okay, so what happens under the normal conditions? So these voltage are determined by the terminal voltage of the generator. Okay, so the voltage at the PCC especially, so they are actually determined by the terminal voltage of the generator itself. Okay, and then the second factor determined by the impedance of the electricity system. Okay, so along the transmission, for example, or distribution example, so they may have the impedance, certain level of impedance, the Z. Okay, the Z load, for example, or the load of the Z, the impedance of the phase itself. And then the third possible cause is actually the current drawn by the loads throughout the transmission and distribution grid. So it can be in terms of V, it can be in terms of Z. So these three parameters, or I itself. Okay. So the system voltage and generation size are generally highly symmetrical. So this is what this something like this disclaimer. So we have said that voltage at the generation side so generally highly symmetrical, or they are actually balanced. So due to the construction and operation of synchronous generators used in large centralized power plants, so we are able to control what is actually happening at the centralized power plant. So in terms of the construction of the generator itself or the operation of the system. So the operation done by the synchronous generator. So therefore, what happened? The central generation does not, in general, contribute to unbalance. Okay, this is what I call a disclaimer. So we have set a standard that at voltage generation, okay, the voltage generated by the central power plant is not the one contribute to unbalance. All right. So what happened next is actually, okay, this is your utility. So this is the transformer to stepping down your voltage of the supply, for example. So this is the point of common coupling, PCC. Okay. So we have another PCC. So we have one group or cluster of industrial customer, another cluster, so the third group of industrial customer. So this is where, all right, basically the unbalance occur. So asymmetry of the load. So we have seen earlier, so we have made a clear disclaimer that at the generation side, so the centralized power plant, so everything is good, everything is symmetry, and everything is balanced. So particularly for the generator voltage. But what happened at the loads? So in most practical cases, the asymmetry of the load is the main cause of this to happen, particularly unbalanced. So at high and medium voltage level, the loads are usually three-phase and balanced. So although large single or dual field loads can be connected, such as AC retraction, so see figure below later, so or induced furnace, so large metal melting systems employing highly irregular powerful arcs to generate heat. So the furnace as well as the AC traction. So for example, this is the K132 kV grid. So your grid line over here. So this is actually connected to your AC railway. Okay, so you have train over here. So this is the tapping from R, Y. Okay, between these two to obtain the line voltage, right? And then go to your railway system. So AC railway connection as an example of asymmetry load connection done at transmission level voltage. At transmission level voltage is coming down to your AC railway connection. So this may occur a symmetrical load connection or unbalance. So identically, if you move on to the furnace, all right. So for example, power just Gurun at Gurun, Kedah, where it operates at 30 kV incoming. So arc furnace as another example of unbalanced or asymmetrical load connection done at high level voltage. All right. So what about the small scale distributor or embedded generation? So however, so we can see nowadays, so where small scale distributor or embedded generation installed at the customer side. So this is the good example. We have the PV collector, the photovoltaic collector, in order to harvest the sun ray or the sunlight and convert it into energy, certain level of energy. So installed at the customer sites has become more popular and taken up significant share of the electricity production. The situation is different. So many of these relatively small units, such as photovoltaic installations, so what I meant earlier, So are connected to a grid at LV by means of single phase power electronic inverter unit. So they are actually connected to low voltage or grid at low voltage LV. So this is connection. So DC AC or inverter. So we have an AC transfer over here. So this is for the protection isolation switch. So this is the credit meter. So we have the consumer unit, the AC power, and then this is how where you utilize the energy at your house, for example. So again, the electricity. So again, the electricity. Oops. Sorry about that. Let us continue. So where the electricity actually supplied to your home through AC socket over here, it may be also refeed to the PCC over here. Oops. So it may get back to the PCC and the grid line or the LV grid line. So connected to grid. So you see over here, so this is the consumer unit. Okay, so it comes from inverter, and then you may use certain level of voltage, and the rest may go to the PCC. So this is another asymmetry load or unbalanced load occur. So the connection point has a relatively high impedance leading to a potentially larger imbalance of the voltage that then is the case for connection at higher voltage level. Okay, and then why an unbalanced system is undesirable. So why it is actually unwanted. So we try to avoid unbalance because first, an induced rotating magnetic field which oppose that of normal rotation. So it may cause, so a significant problem created by unbalance is an induced rotating magnetic field which oppose that of a normal rotation. So we have the opposite, so normal, and then this is the opposite of the induced rotating magnetic field. So what happened next is causing the additional heating in the stator windings and in the iron parts of this stator structure, and in the iron part of the rotor structure as well. So this heat which actually cause the malfunction of the motor. Okay, so it may also reduce the efficiency of the motor in terms of heat loss. Okay, it's allowed to persist in sufficient quantities. So this negative sequence effect can cause severe damage to the generator. Okay, and then from utilities perspective, cost is the main issue. See, so all the unused capacity on unbalanced system using all phases equally maximize efficiency of the system. Okay, so the efficiency of the system may also affected. So also in Y system, okay, for example, star system, so balance load means zero current in the neutral. So we have seen earlier, so where IN equal to 0. So what about we have the asymmetrical system, asymmetrical load or unbalanced loads. So imbalance makes a current flow in this wire. So with a very unbalanced load, it can cause a significant voltage drop since we have a current flow inside this IN. Sorry, IN is, okay, this is in the balance. When it comes to unbalance, this is is not equal to 0. This means there are some amount of currents flowing inside the neutral wire. So imbalance make a current flow in this neutral wire. So with a very unbalanced loss, it can cause a significant voltage drop. So when there is current, this means there's some resistance in the wire that cause the voltage drop to occur and lead to another problems. So measuring voltage unbalance. So how we actually measure gauge the unbalanced voltage? You can simply take out your voltmeter and measure the phases between phases at the load terminal. So it's between R and Y. It can be between R and Y and B as well as B and R. So at the starter terminal shown the figure below. So we can simply measure out the value of phase line current between RY. It shows over here 460, 467, 450. So this is to show how unbalanced they are. And then some quick or some simple calculation on the percentage unbalance. So we have the maximum deviation from average of reading. So you have certain value of voltage, for example, up to 5 for instance of out of this 5. So you must be able to come up with this average reading, and from there again, so you try to figure out the maximum deviation from the average reading, and by that you can actually calculate the percentage unbalance. So some notes over here. So the effect on motors and other devices in the circuit depends directly upon the percent of unbalance present. So this is how significant it is, because some effects on motor and other devices, so they are actually rely or depend on this percentage. Okay. So this is one good example on how we can calculate the voltage unbalance, the percent voltage unbalance. So we have 3 readings over here. So just this is an example. If you go back to your method to measure the terminal voltage, so you come up this value with these 3 values. Okay. But in this particular example, we have a single phase voltage. So 230, 232, and 225 volt. So calculate the percent voltage unbalance. So first you have to calculate the average, of course. Okay, this is the total average voltage. So 230, 232, and 225 over 3. So this gives us 229. So 229 is going to be the average value. So now try to calculate the maximum deviation. So the first value 232, 230, and 225. So 225 become the maximum deviation, which is 4 voltage. Okay, so 229 minus 225 is equal to 4 volt. So from there, so the maximum deviation, which is 4 volt, so divided by 229. So 4 over 229 multiplied by 100%, this is equal to 1.25% in terms of percentage unbalance. So why it is so significant? Because critical equipment, especially motor and their controller, will not operate reliably on unbalanced voltage in a 3-phase system, of course. Okay, and then in general, so this is why this percentage is significant. Okay, over here, because generally the difference between the highest and the lowest voltage should not exceed 4% of the lowest voltage. So this is the tolerance. So value 4%. So it must be not exceed the 5% of the lowest voltage. So greater imbalance may cause overheating. Okay, this is the what I call it, the more greater effect if you have this to persist consistently. So it will cause you the overheating of the components, especially motor, and intermittent shutdown of motor controllers. So where motor operator on unbalanced voltage will overheat, and many overload relays can sense the so you may fail the release, okay, the overload relay, the protection system, so they can actually sense the occurring of the overheating, and will of course damage your motor, the equipment, etc., etc. So exercise 3.1, so this is very simple. So you have these 3 values, so you need to calculate the average, for example, and then find the percent voltage unbalance. So frequent causes of unbalanced voltage in LV display system. So what happens if you have this unbalance happens quite often? So malfunctioning equipment, including blown capacitor fuses. Okay, so this is quite common. So unequal impedance in conductor of power supply wiring. So unequal impedance. So this may also happen at the location of your power supply wiring. Okay. So next, unbalanced distribution of single phase loads such as lighting. And then, so this is one of the common heavy reactive single phase loads such as welders. And then the large heater control that cycle rapidly. So effect of voltage unbalance in LV. So what about if you have the voltage unbalance, and what the effect may give to the LV, the low voltage distribution system? Again, so it can create problem for polyphase motor. So the main effect of voltage unbalance is motor damage, okay, due to excessive heat. So for example, so voltage unbalance of 1% of the 20. So this is what I explained earlier. So this is very important to have the percent voltage unbalance. So for voltage unbalance of 1%, so this is the limits. So at the terminal of a fully loaded motor can result in phase current unbalance of 6 to 10%. With only 1% voltage unbalance, so it may cause the phase current unbalance of 1 to 10%, which raises the operating temperature of the current of the motor. Sorry, so the higher the current, so may cause the higher heat. Okay. Higher heat. So the operating due to the operating temperature of the motor. So reduce heat energy efficiency. So in terms of efficiency, is may reduce and shorten its lifespan. So unbalance in power system may cause excessive drawing of reactive power. So this is again what we have gone through earlier. So reactive power. So it's draw much excessive reactive power. So malfunction of the pressure, equipment, maloperation of measuring instrument, and shortening the lifespan of different appliances. So current unbalance in three-phase circuit increases net current. So net current in some phases. So it may, on the other hand, decrease net current in other phases. So this result in unequal loss in phase and unequal heating. All right. And then in ungrounded system, what happened to the unbalance? So what happened to the neutral? So unbalance causes neutral shifting. So this hampers accurate operation of relays. So relays also may affected. So the circuit breaker also may affected. All right, so another subtopic, 3.2, analysis of unbalanced load in three-phase system. So unbalanced data connected load, so unbalanced 4-wire star connected load, and then finally unbalanced 3-wire star connected load. So as was mentioned earlier, so one of the main causes of voltage unbalance in LV distribution system is the unbalanced distribution of phase loads, okay, such as lighting. So we will next analyze voltage and current relations in three-phase circuit. It is the following types of unbalanced load. Again, unbalanced load, right? So unbalanced data connected load. So 4-wire star connected load and 3-wire star connected load. So unbalanced data load. So similarly, just like the balanced data load, so you should have the similar configuration over here. So where you have your R phase, Y phase, B phase, as well as the line current over here, and then you have the phase current IRY, so RYB as well as BR. So where in the beginning, so we have the VRY, so this is coming from the generation, the source. This is equal, okay. This is balanced. This is symmetrical, okay. But we come to the load ZRY, ZBR, and ZYB. So they are unequal. So they are in unbalanced. Okay. Therefore, okay, when we come to VIR, the Ohms law, of course, when you have R which is unbalanced, okay, unbalanced, I put it cross for example, unbalanced, so that makes I also unbalanced. Okay, so RY is not equal to IYB, is unequal BR. So when the phase is not equal, of course, the value of line is also not equal. Okay. So example 3.2, so we have again, so this is the data connected load. Okay, so we have ZRY, ZYB, ZBR. So all three, these are not equal. So not cross, but this symbol is better. Okay, so they are not equal compared one to another. So find the phase and line current, assume RYB sequence. So taking VRY as reference, so taking what? VRY as the reference. So we have the first V over here. So this is the VRY. So taking this as your reference. Okay. So we can write, so VRY equal to 400, 0, YB, VR. So again, so these are balanced. So we have made a declaration. Okay, so we have set the standard. So we have made the disclaimer, whatever you like to call it, where the source, okay, is always balanced. Okay, so simply differentiate between the phase between one to another by 120 degrees. Shift them by 120 degree. So on applying Ohm's law to the impedance, we get, so this is what it means. Ohm's law, I equal to V over R. After you rearrange it, so substitute the value of each particular Z or each respective Z. So you may get the different value of phase current. Okay. And then the various line current in the data load R. Okay. So Ry equal to, again, so this is Ry equal to Ry minus IBR. Okay, it's stated over here. I equal to Ry minus IBR. Again, substitute the value you have just obtained, and this gives you this value of IR. So identically for IY, so we have IY over here. So this is equal to IYB, okay, minus IRY. Okay, so IY is equal to IYB minus IRY. Substitute everything, and then you may get IY equal to 39.85, 136.59 degree. So similarly for IB, so you have IB over here. This is IB all the way up here, and then we have IBR, so minus the coming YI, which is IYB. Okay, so we have IB equal to IBR minus IYB. Okay, so we will continue our example 3.3 in the next video. Again, thank you very much for your attention. See you.